Hello students, welcome back. Let us resume our discussion in section 3, Möbius function. Möbius function does not really have a great standalone value, to tell the truth. That's why I didn't talk about it in section 1 as typical examples of arithmetic functions, but it works well for other arithmetic functions. Like this. Whenever we have a summation, you can invert it using Möbius function. And we're going to use this Möbius inversion formula to prove the next theorem. Small f and capital F are related like this, yes. Same as the condition of this Möbius inversion formula. And if capital F is multiplicative, then so is small f. Remember this? Theorem 1.5, same condition. If small f is multiplicative, then so is capital F. We proved it. It wasn't easy, but we proved it. And we went through some corollaries. But here we are going backward. You're proving the converse. So if you put together 1.5 and 3.5 together, then we can say, under this relation, if capital F is multiplicative, if and only if small f is multiplicative. You can say that. One direction, small f is multiplicative, then capital F is. That's something we already know, we already did. For small f, we're going to use Möbius inversion formula. Okay, suppose that m and n are relatively prime. F of mn, and then let's just put it into Möbius inversion, this one here. D dividing mn, mu of d, capital F of mn over d, all right? And d dividing mn means d can be decomposed into some a times b. A divides m and b divides n, ab, where a and b are relatively prime. And that's something we did in the proof of 1.5 as a matter of fact, but I don't want to go back there and then go through with all that ordeal again, because that was a significant achievement we did. So believe me, we already did that. D can be decomposed into a times b. A divides m, b divides n, and a and b are relatively prime, so that we can use this multiplicative property as we did in 1.5. So okay, go ahead and do that. Mu of ab, mu of a times mu of b, and capital F of mn over ab, capital F of m over a, n over b, using the multiplicative property again. Now it's pretty clear what to do. Decompose for a part and b part separately. So a divides m for mu of a, capital F m over b, and then b divides n, mu of b, capital F of n over b. So a part here and b parts there separately. Then that happened to be m part and n part, thanks to this Möbius inversion formula again. F of m times f of n. By the way, I have some time left, so I'll give you this d decomposed into a times b. Let's go back to 1.5. This. A and b are relatively prime, and d divides mn. And then there exists unique pair of integers a and b, so that d is a times b, a divides m, b divides n, and they're relatively prime. Remember that? From the fundamental theorem, m and n can be written as prime factorizations, and they do not share any prime factor. M times n, just written all the way like this, no sharing, so they're all distinct. And then the divisibility, and we have just all prime factors, all p's and all q's, with appropriate powers, less than or equal to those m's and n's, respectively. Some of them may hit 0, but no negative power, of course, and they do not exceed any of those m's and n's. Define this as A and that as B, then A and B do not share any prime factors, so they are relatively prime. And the powers are all less than those of m's, and powers are all less than those of n's. So A divides n and B divides n, we get everything. So this decomposition is one of the core steps, the key technique that we use to prove this theorem 1.5. And theorem 3.5, well, we're talking about multiplicative property for same condition. So it's not surprising that same technique is being utilized here. Again, of course, we want to use this Möbius inversion. And Möbius inversion, and then decompose D into A times B to separate out. And use the multiplicative property of mu and capital F. Once we have the first line using all the properties, from this point on, it's easy. All the A part on one side, all the B part on the other side, separate those out, and then we have multiplication f of m times f of n. So that completes the proof of the multiplicative property on the summation, the second part. So what can you say? If you have this relation, capital is multiplicative, if and only if small f is multiplicative. Let's see. Martin's conjecture, is that something worth discussing? No. That's it. That's the end of section 3. And we're gonna meet again in section 4 in a separate video. See you later.